Good morning, everyone. Let's see, let me put the pictures down. Okay, so I've had a student contact me in the meantime, between yesterday and today, and we talked a little bit about the assignment. The assignment, as I look back, was pretty stiff, pretty long. These are not short problems to do. So maybe this can be more, I don't know, of a review, a question period than anything else. I don't know. We'll see what happens. So I've got up here, this is from the previous, this is from the 4.2 lesson. And I'm going to open it up to questions. Problems on the 4.2 assignment that you would like to go through. So anybody out there, problems on 4.2 that you didn't get to or you'd like to see an example of? Well, I'm gonna, nothing, huh? Okay. And I didn't get any official requests from email. Oh, we got one here. I have a few. One moment. Okay. We got something coming in here. Number 99. All right. 4.2, number 99. So let's start with that one. Okay. So let's just go to the book. Number 99. Trachea contraction. Let's just make a copy of that. Okay, let's stick that right here. Okay, so let's see what we got here. Coughing forces the trachea to contract, which affects the velocity of the air passing through the trachea. The velocity of the air during coughing is, and then we've got this equation where R is somewhere greater than or equal to 0 and less than or equal to capital R. Capital R is the normal radius of the trachea, K is a constant, and R is the radius during coughing. What radius will produce the maximum air velocity? Okay. So let's see what we got here. Put our equation down. Yeah, and we don't know what the normal radius is, so okay, let's just write this 0 less than or equal. So we don't have numbers for all of these. All right. So we want maximum velocity, and we've got an equation for velocity. Therefore, we need to take the derivative. Okay, so v prime. should we multiply this out? I think I will. So this would be KR minus K small r times r squared. Should I multiply that out too? Let's try it. Okay, so that's not the derivative. So let me change that mark there. These are just other expressions for the velocity. All right, so now let's take the derivative. Okay, K is a constant. So we've got, and really capital R is a constant too. We just don't know what it is. So we take the derivative, we get 2K capital R small r power rule minus 3K R squared. Okay, now at a maximum, which is what they're asking us for, maximum, we should be able to set that equal to 0. We know that at a maximum, there should be a horizontal tangent. So 0 equals, let me get my keyboard out of here so I have a little more room to write. So 0 equals 2K R minus 3K R squared. We set this, we would add 3K R squared to both sides. All right, now we can what? Divide both sides by K. Divide both sides by R. And then what are we trying to find? We want the radius, so that would be the small r. Okay, it's got scrunched up down there. That's about as good as we're going to do because we do not know capital R. And so now we know what? When the, let me make sure I get the, so R is the radius during coughing, small r. So when the radius during coughing is 2/3 that of the normal radius, that's when we're going to get, according to this, the maximum air velocity according to that equation. Okay, I've got now from the test person, I can't remember who you are, test person. I also, did anybody have any further questions on 99? So 66 and 73 are next. Okay, we got another one coming in via the text message. Let's see what I got. $35 is another one. So let me make sure I get these all down here. Okay, we've got 66, 73, and I also got a 35. All right. Well, I don't know. Should we take these? We'll try them in numerical order here. Let's do number 35 next. Okay. So let's scroll to a place where we're closer here. Let's go over here and let's plug in 35. Okay, 35. All right. So 35, I need to grab this. Oh, I need to grab this. No, I need to grab this. 35. The escape key, I need to have the keyboard back on. Okay, so I'm sorry, I'm having a little trouble here. Okay, so back to here, 35. Okay, finally copy 35. Copy image, come back here, paste. Okay. So, and now I got to look, what are the directions above that? The directions say in 24, find the critical numbers, if any, find the open intervals on which it's increasing, decreasing. Okay, and then check it out on your graph. All right. So, let me come back here. So, what do you do with an absolute value problem? Well, it's really in two parts, right? You've got f of x equals 5 minus, that's taking it as a positive value. And then you've got, so it's either that or, and on the other side, you've got 5 minus, and now you've got the negative of that, which is negative x plus 5. All right, so derivative. Well, that's a constant. That's, I mean, here, let's just rewrite. Let's first rewrite the function. So rewrite the function. We've got 5 minus x plus 5. So this really turns out to be 10 minus x. And on the other side, this function can be written as 5 plus x minus 5, which is just an x. Okay, derivative. Okay, the derivative, where was I? So the derivative of this is just what? Negative 1. And the derivative of this one is just 1. Okay, so we've got these two derivatives. Let's take a look at the graph. 5 minus the absolute value of x minus 5. Here's what the function looks like. You can see we've got from when we're to the left of 5, we've got a positive 1 slope. When we're to the right of 5, we've got a negative 1 slope. And the question was, when do we have a maximum? And that would be at 5. Let's see. Just looking back at the problem. So apply the first rule. Yeah. So anyway, that's kind of a special problem, but that's the way that one amounts to. Now, number 66 is next. Number 66. Let's find a spot. Okay, 66. Let's find it. So, finding and analyzing derivatives using technology. Use a computer algebra system to differentiate the function sketchograph. Okay, so number 66. Let's grab it. And you know what? I'm going to grab the directions with it. So let's get rid of that. Go back. Grab. So we're supposed to pretty much use a computer to do this one. So copy. Okay. Paste it in here. Okay, so now some of this, I have to admit, I haven't shown you how to take a derivative using Desmos, but anyway, I'll show you how to do it. All right, so 66 is the one we're doing. So I suppose we could, what, multiply that 10 out? And then it would read, so after we do this on the computer, sketch the graphs of f and f prime on the same set of axes. Okay, so let's, let me write this down. 50 minus 10 times the square root of x squared minus 3x plus 16. And then let's go to Desmos. Okay, here we go. So we've got 50 minus 10 times the square root of x squared minus 3x plus 16. Okay, so you can see there's our graph. It looks like it's a pretty normal parabola. All right, now I should have done this. You can set it equal to f of x, and then let's see. Can we just do f prime of x? I'm trying to remember. Yep. So there's the derivative, and now I've put them on the same screen. Okay, you can see how this. See, up here you can see we've reached a maximum. Okay, and that means the derivative is the slope of the tangent, and the derivative, as you can tell, is horizontal. I mean, the slope of the tangent is horizontal, and sure enough, the value of that slope is 0, and you see right below it. Directly below it. So anyway, the black curve is the derivative. Now, back to the problem. What are we supposed to do? Find the intervals on which f prime is positive and the intervals on which f prime is negative. Yeah, so we've already compared the behavior of f and the sign. You know, let's look at one more thing on here. Okay. Let's see. So where is the derivative? Where is the black curve positive? And the answer is anything to the left of, what is that, 1.5? It's positive. So, and if you look on the purple graph, when is the slope positive? Anything to the left of 1.5. So you see how that matches. When is the slope on the purple curve negative? Whenever we're to the right of 1.5. Look at the derivative curve. You see, when is it below the y-axis? Anything to the right. So anyway, that's how that compares. So now, what was the thing we were supposed to do? Oh yeah, when is the derivative well, we just answered it, but when is the derivative when is the black curve positive? When x is less than 1.5. When is it? And then they ask negative. Yeah. So that's pretty much the analysis of, what was that, number 66? Number 66. Oh, all right. So now that I'm done, you wanted to do 65. Okay. Wow. All right. So let's go back and do 65. 65. Back to the book. So same kind of a concept. Let me quick grab that. Oh, we already have that, don't we? Yeah. So we can use, I've got it right here. Okay, let's do number 65 now. So this was 66, 65. Okay, so f of x equals 2x times the square root of 9 minus x squared. And we're looking at the interval from -3 to +3, closed interval. Okay, let me write that down. 2x times the square root of 9 minus x squared. Okay, come over to Desmos. And f of x equals, redefining it here, 2x times the square root of 9 minus x squared. All right. So you can see that's what our function looks like. And then we can do f prime of x. I thought. It's not doing it. All right. You know what? I'm going to use g of x just to would be less confusing here. There we go. So now in red, or whatever color that is, that's the original function. In blue, that's our derivative. So one more time, what were they asking us to do? We've drawn the sketches of both graphs on the same set of axes. We've done that. Find the critical numbers of f in the open interval. So what are the critical numbers of the function? So remember, the function's in red. Well, critical numbers are anytime what? The derivative equals 0. And according to this, that would be there and there. Those are the derivative. And why is that? Because at that point, we're at a minimum. And at this point, the reason that's a 0 is because we're at this maximum up here. Okay. We don't have any, what, non-differentiable points, so that's the end of that part. And what else were we supposed to do? Compare the, yeah, we've already talked about, compare the behavior of f and the sign of f prime. So let's just do that one more time. So when is the function going uphill? When is the red function increasing? Anywhere between this point down here and this point up here, right? That's when it's going uphill. And you notice on the graph, what's going on with the derivative between here and here? Oh, it's above, it's positive, it's positive. That whole thing is positive. That makes sense. When is the function decreasing? From -3 down to here. And sure enough, from -3 up to -2, notice the blue, the derivative is negative. Negative curve decreasing. Likewise, when is it decreasing? over here from 2.121 to 3. What's the blue curve doing from 2.1 to 3? It is negative. So that's just reinforcing a negative derivative means a function is decreasing. A positive derivative means a function is increasing. Where are we? So 73. So I've got 73 and I've also got a 75. Is that correct? So 73, 75. Let's look at 73 next. All right, 73, book. Here we go. Let's close this. I'm sorry for these flashing around here. Let's grab number 73. I'm going to grab this whole thing so I can get the directions with it. Okay. So let's take a look at 73. In exercises 73 and 74, use symmetry, extrema, and zeros to sketch the graph of this function. How do the functions f and g differ? All right. So let's take number 73 and let's play around with this. So we've got x to the 5th minus 4x cubed plus 3x. All right, and then we'll leave g alone for just a minute. So, and then that is over x squared minus 1. Okay, well, I can take what? An x out of the top. I can factor the bottom. Can I factor that top? I'm pretty sure I can. What is that? X squared. And plus 4 minus 1. So gotta get a little more space here. Okay, so and this can be factored even further, right? So I ran out of space. So this is x squared plus 4. And this is x plus 1, x minus 1. So that's the top fully done. And then we got x plus 1, x minus 1. And of course, we can do this. All right. So we've got that down to, wait a second, did I factor that right? Plus 4. Let's see, x squared minus 4x squared. You know what? I did it the wrong way. It's minus 4 plus 1. Hang on. Let me double check this. I got to be more careful. My apologies. Okay, so that's x times The 4 has got to be negative, doesn't it? So x squared minus 4, x squared plus 3. So when you multiply x squared times x squared, you get x to the 4th. And then you've got x squared times 3 is 3x squared. And negative 4 times, no, that's not going to work either. Hang on, it's 4 and 1. A little rusty here. Hang on just a minute. So, plus 1. I'm having a little trouble here. Let's see, x squared minus 4, x squared plus 1. That would give us a minus 3, so that won't work either. Okay. I guess that can't be factored on the top, so at least I can't see it right now, not in the middle of being online here. All right. So let's at least take a look at this. As you can tell, there are 2 illegal values on the bottom. Okay? So you can see that x cannot be equal to negative 1, and x cannot be equal to 1. What would it take to make this thing equal to 0? Zeros. Well, x is 0. We'll make the whole numerator 0. Remember, to make something 0, we can only look at the numerator. So x could be 0. And then, if this thing could be equal to 0. So let's just check that out. So that is, I already tried factoring that. Let me think about that. Negative 3, negative 1. That's it. Okay, I figured out the factoring now. X times x squared minus 3 and x squared minus 1. Because in the middle, you're going to get negative 3x squared plus a negative 1x squared, which would be a negative 4x squared. Okay, I got it now. And then on the top, x squared minus 1 is x plus 1x minus 1. So now you're down to, this is the expression, x times x squared minus 3. Now, if you look at the other function, that's exactly what they've got. And so the question is, what's the difference? They come out the same. And the difference is, in the expression of the top, x cannot be 1 or negative 1 because it's in the denominator. So let's take a look now. Yeah. So then we're supposed to make a graph. Well, that's going to take a while. Let's do the Desmos here. Let's see. I got to write these down. So we got x to the 5th minus 4x cubed plus 3x all over x squared minus 1. And it may not show up. I don't know. And the other one is x times the quantity x squared minus 3. Okay. So now Desmos. So parentheses x to the 5th minus 4x cubed plus 3x, all divided by x squared minus 1. Okay, yeah, you won't be able to see this on the graph. So there's the there's the f of x. And the g of x is simply x times the quantity x squared minus 3. And you notice they are identical. the only thing the only thing that's different is that first function, and you can't tell it here. 1 and -1. Where are they? Yeah, that point is not on. So 1 and -1. This point is vacant on this graph. You can't tell it. There's a hole there. And likewise here at -1, that's a hole. I'm sorry, I got the wrong spot right there. That's a hole. So it's kind of a silly, I mean, there is a difference between these two, and that's very important, okay? This is not the same as this, even though it simplifies to it. You must make the distinction that on the original function, on that one, x cannot equal 1 and -1. So that's really what it comes down to. Otherwise, they're identical. So what was that? That was number 73. Okay, now somebody asked me about 75? I believe so. Okay, number 75. In exercises 75 to 80, the graph of f is shown in the figure. Sketch a graph of the derivative of f to print an enlarged copy of the graph. Okay, so let's see. I'm going to grab that. It's not going to be much of a graph, but let's do it. Copy. Okay, come back over. See, I should put a number here. Well, we know that was 73, but so now we're doing number 75. So that's the function. What's the derivative? Well, what's the derivative of a horizontal line? It's 0. So it's not very interesting, but that's the derivative. Because forever, the slope of the tangent line is 0. So, I mean, that's it for number 75. So let me go back. Where are we? 66, 73. So I did 30. I think I've done the ones that are asked. Did anybody? I'm having trouble keeping track of things here. I got, let's see. Let me look at my text messages again. $35. 99. I think I've hit the requests. Did I miss anybody? I'm going to take a look. All right, I'm going to go back and I want to take a look at number 17 and number 19. Those were kind of challenging. So I'm going to add those to the list. So now whoops. Let's leave that where it was. I'm just trying to think. Yeah, let's go up here. Okay, so let's do number 17. So, number 17. First page. Yeah. No, that's not right. Okay, here we go. So the directions on number 17 were identify the open intervals on which the function's increasing and decreasing. Okay, so all we got to do is find those intervals. So in order to find that out, we need to do a derivative, right? And we need to find out when the derivative is positive and when it's negative. And so in order to do that, we need to find out if there are any points where the derivative is 0. Okay, so take the derivative. So what happens when you try, let me change this back to black again. So what happens when you take the derivative of an e? It's itself. And then is there a chain rule here? Yes, we get a -1. So I'm just going to solve that by putting a negative out in front. Okay, second part, e to the 3x itself. And there's a chain rule again. 3x is a 3. So there's our derivative. And now we could what? Factor out? I don't know if we, yeah, why don't we do that? So we know this is going to be set equal to 0. So let's factor out what? An e to the x? I guess let's just leave it. I'm going to take this approach here. All right, let's add e to the -x to both sides. So 0. Why set it equal to 0? Because we are trying to locate the points between increasing and decreasing. Add e to the x, e to the -x to both sides. There we go. Now, let's divide both sides by e to the -x. So basically, here's what I'm doing. So on the left, we're going to get a 1. On the right, what do you do when you divide numbers with the same base? Keep the base and subtract the exponents. What's 3x minus 1x? It's actually 4x, right? Ah, forgot my e. Let me write that down. So e to the 4x. All right. So now I'll divide both sides by 3. And now we want to get that exponent out of there, so we're going to take a natural log. The natural log of 1/3, and the natural log of the right side is just the exponent 4x. Okay? Divide both sides by 4. And we found a critical number. And then you can go ahead on your calculator and work that out. It turns out that's negative, trying to get my pen to work here, negative 0.27 is what x is. Okay. So now that we've found that, I guess, yeah, let's just take a look and see if that agrees. I forgot what we were trying to do here. 17. Directions on 17. On the bottom here, which ones are in? So when is it increasing? When is it decreasing? Okay, got it. So let's just take a look at this. This is e to the -x. Here it is. Plus e to the 3x. So here's what it looks like. And right there, that's the point we found, negative 0.27. So we found when it was at 0. The derivative was at 0. And then if we would just pick a number to the left of it, we would see it would be negative and it would be decreasing, and everything to the right of it is increasing. And that's basically number 17. Okay, and then I wanted to look at number 19. Number 19, how are we doing here? We got 5 minutes. That should work out just about right. Okay, number 19. Grab the problem. Okay, so the same deal. When is this thing increasing and when is it decreasing? So we need to find the derivative. All right. We always seem to have a little trouble with logarithm derivatives, so I thought this would be a good one to look at. So anyway, f prime of x. So what we have here is basically a product rule. So the first times the derivative of the second. Now the derivative of the second is what? The reciprocal, it's 1 over that. So that's just going to be 2 over x. And then we have a chain rule. This is really what? A 1/2 x. And the chain rule says that you got to multiply that by 1/2. Okay, so that's the first times the derivative of the second plus the second times the derivative of the first times 2x. Now we want to set that equal to 0. And you know, what can this be simplified to right here? Well, the 2's cancel in the 2 and the 1/2, and you just get x squared over x, which is x. So we have x plus 2x natural log of x over 2. I just stuck the 2x in the front. All right. So now we can factor an x out because we have 2 terms in that big old thing. Take an x out and we have a 1 plus 2 times the natural log of x over 2. So the first thing we can do is say, well, that's a critical point, x equals 0. And then we can also say this other, let me erase that. So this other part could also be 0. 1 plus 2 times the natural log of x over 2. That can be 0 too. Now when can that happen? Well, we could subtract 1 from both sides, and we'd have 2 times the natural log of x over 2 equals -1. Then we could divide both sides by 2. Natural log of x over 2 equals -1/2. And then, so what's the natural log of, let's see. So basically what this says is e to the -1/2 power equals x over 2, right? Isn't that what a natural log is? The natural log of something says, hey, when you take e to this power over here, it's going to equal that thing. And then we can solve this. We can say x equals 2 e to the 1/2. So that's going to be a critical value too. Don't forget, we have this one up here. We have this, that's one, and here's another one, and in decimal form, this turns out to be 1.213. So now you just set up, you've got a fence point at 0, you've got one at 1.213, and now you do your test values. Now, this is kind of interesting. When you do your test value for left of 0, you can't do it. And here's why. If x is less than 0, here's the problem. You look back way up to the top. If x is negative, what's the net? And we have a negative over 2. That's a negative. What's the natural log of a negative number? And you can't do it because e to any power is positive. So basically, we don't have anything to the left. There's nothing out here. So, you know, I'm just going to say it can't be over here. So then you try a number between, and you find out this is negative. decreasing. And when you take a positive, when you take this one over here, it turns out to be positive. So the bottom line is, when you take a look at 19, it looks like this on Desmos. That's this one up here. So you see how it never gets to the left of 0? Just like we said, it just can't be. And what did we find was the other critical power? 1.213. Yeah, right there. So that's where it's 0, and you can see it's decreasing in between 0 and that, and it's increasing after, just like we found out. It's decreasing in between, and it's increasing, and it can't be over here. So anyway, there's another example. Okay, now I got to check back. What's going on here with comments, questions? Okay, well, we've reached our time. Thank you for your attention. One more day on the assignment. I will see you tomorrow.